Okay, hi and good morning everyone. So for today, basically, I will be continuing the second part of the second chapter, fundamentals of image processing. So the outlines for this particular videos will be the second half of the previous slide. So in this video, we will talk about the second half from the pixel, the instances of pixel itself, and we will talking about the basic mathematical tools, whereby we do have the plus this and that, and spatial operational. So whereby we will talk about the three types of things, pixel, a group of pixels, and while this one is geometrical. Okay, all right. So we straight away jump to the first one is regarding to the pixel. So in this slide, we would like to introduce you the how the pixels is coordinate in such a way from the top left corner of one images. So imagine that we have this, right? So the idea of starting the to count the images is happen with the x, and this would be the y. Okay, right. So imagine that this would be x and y. Okay, so the center of this how many was it? 9 is centralized by xy. So this one would be x plus 1 with y. Sorry for that. So this one is x plus 1y. So this one is x y plus 1. So while this one x y minus 1. So while this one is x minus 1 y. So whereby the what we call it, the straight connected pixel, whereby it will be like this. Okay, two horizontal and two vertical neighbor with coordinates, what we call it 4 neighbors of P. So how we do it, basically P is the center, and the surrounding pixel, what we call here is Q. So this is the Q. So meanwhile, the NP4 is a set of the Q centered by P. Okay, so whereby this is the value of Q. Let's say this is Q1, Q2, Q3, and Q4. So this to this, this to that, this to this, and this to this. So that would be 4 neighbor. Okay, here we call it as N for P. So reflected by the blue arrow. Okay, so the second one is the diagonal neighbor of P. So for this time around, basically we will see how the location of this particular diagonal pixel. So here we have this, and that, right? So the center here, x and y. So how about this, guys? So this is x1, y minus 1, right? So this one is x plus 1, y plus 1. So how about this one? So this one, x minus 1, y minus 1. So this one, x minus 1, while y plus 1. So then this 4 neighbor diagonally is stated over here. So we have another 4. So this time around, the neighbor for diagonal from P to Q is known as NDP. Okay, so now we have two things. One regards to this one. The other one is this. Okay, NDP and N4P. Okay. Okay, so Another way around to see more than that. So if we take a look at the combination of N4P and NDP, so basically we can call them as 8 neighbor guys of P. So meaning 1, 2, 3, 4, 5, 6, 7, and 8 denote as N8P. Okay, blue arrow and red arrows, right? So means the combination of 4 P and 4 diagonal of P, right? So we have now we know that we have N4 P and DP and N8P, right? Okay, so we straight jump to the next one. This the set of images location for the neighbor of P is called neighborhood of P. So this becoming like this. So we have this 4 location plus this 4 location. So becoming set, right? So this one is what we call it neighborhood of P set. Okay, everything we have 8 location or 8 coordinates, right? So the neighborhood is said to be closed if it contains of P. So meaning if it contains of P, then it been said as a close, and the neighborhood is said to be open when excluding of a P itself, right? Okay, so that would be a bit thing or relationship between the pixel to the neighborhood. Okay, right. So the next thing we would like to discuss about the adjacency. In a normal perspective, basically, we might say that the image that we use, okay, say that we have 2 images over here. So this one is a 1-bit image and this one is 8-bit image. Okay, so this one is 1-bit black white image. This one is 8-bit grayscale image, right? So in this particular image, the behavior of the image is the same, width and height. However, so the things that related to how the pixel is presented by itself is regards to the bit has been chosen for this particular image. Likewise, this is 2 power 1. So meaning the value for each of particular pixel only have 0 and 1. Okay, so there are only 2 value. Okay, for this one, we have 0, 1, 2, 3 until 255. So there will be 256 value in that particular range of intensity. So that would be the idea of differentiation between these two. Okay, right. So normally to describe the adjacency, we might use a set of V, okay, a set of intensity value. So this is intensity value regards to this value, guys. Okay, used to define adjacency. Okay, in a binary image, okay, see, so in binary would be this particular example, okay, whereby V is 1 if we are referring to adjacence of the pixel with the value 1. Okay, right. So let's say in one images, we have 3 times 3 pixel. So we have 1 here, 1 here, 1 here, 0, 0, 0, 0, 0, 0. So this is 3 times 3 pixel of 2-bit of 1-bit binary image. Okay, so the idea of talking about this adjacency is how we connect the each of the one value. So like this. So this one is one connection. So whereby this one is one connection, right? Or it could be this connection too, right? So because of the V has been given to us as only 1, so not included 0, unless it has been stated as V equals 0 and 1. So therefore, if we are going to solve this particular set been given, let's say this is 0, 1, 1, 2, 2, 1, 2. So here we can say that the adjacency for this particular example is this. It couldn't be green. This, and that. Okay. Or how about this one here? Okay, let's say we put it 2 here. So we have 3 kind of adjacency for v equals 0 and 1. So while this one is v equal 1, so we have only 3 connection. Okay. So in order to say that this is 4 adjacency and 8 adjacency and m adjacency, so basically there will be the reflection of how it has been connected. Okay, 4 means it reflects to the one that we discussed before, so the close neighbor. So whereby the connection of 4 adjacency is 1, 2, 3, and 4. So that would be 4 types of 4 adjacency. Okay. So if you're talking about the 8 adjacencies, okay, so there will be diagonal one. So including 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So that would be the connection of 8 adjacency. Okay. So while the m, so this one is the first type, this one is second type, while this one is the third type. Okay, the special thing happened here when we talk about m adjacency, whereby the q is np and 4p. So meaning the q is basically here. Okay, so this would be one requirement in order to get the m adjacency. Okay, so q is ndp. So q is ndp again. Q is ndp is this one, right? Q, 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 P. Okay. Or Q is NDP and the set. Okay, so right. So the set of this and this has no pixel whose value are from V. So whereby if we are talking about M adjacency, so this value and this value has no pixel. Means how to say intersect. We can say in the layman terms, it cannot be same as in here and here. It's not exists at the same particular 4 adjacencies and 8 adjacencies. So that would be the idea, right? Okay, so now we will talk about the what is the way that we want to say adjacency for this given 3 times 3 pixel, right? Okay, so here this will be the example, and say that we have this dashed line as this. There will be example number 1 and this one is example number 2. So right, okay, so which one is 4 or 8 or m adjacency? Okay, so I think you guys would be understood about what we have over here. Okay, so 4, 8, and m. So this particular example in the middle is basically having this. This is 4, right? So this is 4 adjacencies. This is 4 adjacencies. While this one is 8. So this one is 8. So meaning every single things happen here is 8 adjacency. Okay, right? Because of the all connected dash line is happen to be majority of them is 8. So while this one, this, and this happen to be okay. Remember about NP4 and NQ4. Sorry, N4Q3 again. It's not like this. N for P and N for Q. So meaning there will be no pixel. So here it is not connected, right? So only this dash line is not exist. So whereby this would be known as M adjacency. because they don't have the intersect of NP4 and NQ4, right? So that would be M. So how about 4 adjacency, guys? So for this, it will be optional and it will be independent for us. So if we try to do ourselves, this one is, oh sorry, it couldn't be red anymore over here. So I will be giving to you as this. So this is 4, guys. Okay. So another way around is when we talk about this, this is 4. Okay. If we have the dash line over here, right? So that would be the idea of describing the adjacency for 4, 8, and M. It depends on how the behavior of the adjacent based on the 3 types, right? So this one is some exercise to be done by yourself at home. So remember the one that I mentioned earlier. So V, it could be 1 regards to any one number in binary pixel connected to each other. So say that in this particular exercises, we have 0 and 1. Okay. So meanwhile, every single thing happen in the interconnection of adjacency is regards to 0 and number 1. Okay. So meaning to say that this, and this, right? Okay. So compute the length of 4, 8, M between MQ. Okay. The length of the shortest. So meaning if we have the particular, if a particular path does not exist of these 2 points, explain why. Okay, right. So you need to explain why does it happen. Okay, then again, if we talk about 1, 2, okay. So now follow the blue line. So 1, 2 is different, guys. So I just put it this way. 1, 2 is regards to this area, guys. Okay, so that would be different way because they are skipping the 0 and 3 for this one. So while this one, for this one, they skip 2 and 3, right? So it depends on what is the step are given to describe the adjacency. Okay, so yeah. Okay, connectivity. Okay, here we might see this path, guys. So basically this path is in this particular slide. Okay, a digital path or curve from P to coordinate Q. All right. So P to Q. Example. Is the sequence of distinct pixel with coordinate by n, so meaning this go to here and this go to that. So where the xi and xi minus 1 are adjacent of n. So this will be normal statement. Say that we have, okay, let's say we have 3 over here. So meaning, so this is 1. Okay, because of I equal 1, 2, and 3, right? So 3, it could be until 2 lah. Okay, 2, y also 2, and it could be, when we talk about 2 is 1 and y1, and it could be 0 and y0, right? So that would be the idea of adjacence. Okay, so if the xo and xn, the path is close, so we can define that the okay, if x0 and xn, the path is close, meaning to say that the relation between 0 to x1, y1, the interconnection is called as a close one, right? Okay, so now we can define the 4, 8, and m path depending on the type of adjacency specified, right? Okay, so to do this, we have the 3 things to be discussed, A, B, and C. Okay, the path for 2.28b between the top, okay, between the top, where is the between the top one? top right and the bottom right are the 8 paths. Okay, right. So either way, we go to here and here. So basically, they will be using the 8 paths because 8 is describing as this particular neighborhood, right? So while this one, C, is describing the this and this without the intersection of N4P and N4Q. So whereby we did discuss about this just now, I think over here. Okay. So we also can describe this as N path, okay, instead of 8. Okay. So this one is 8 and this one is M. Right. I think that will be clear example for you guys. Okay. Now we are going to the connectivity and region. So yeah, connectivity and region. Okay, so let S represent a subset of pixel in an image. Okay, S is subset of V. Okay, oh sorry. Okay, so two pixel P and Q are said to be connected in S if there exists a path between the consisting entire of pixel in S. Okay, if there exists path between them, okay, in S. For any pixel P in S, the set of the pixels are connected in S is called connected component. So anything connected with the set in S with P is connected. If it only has one component and that component is connected, then S is called as connected. So even though there will be at least one component, so there will be known as connected one, right? So that will be connectivity. Okay. So say that we have another subset called R. Okay. We call R region of the image if R is connected. Okay. R represents the subset pixel of an image. So this also known as S in the previous paragraph. So while this one is R. So this will be the subset, same. Okay. We call R a region of image if the R is connected to a set. Okay. So meaning example this. So this one is R1, so this one is R2. So R1 and R2 is in the R. Okay, that would be the idea. So two regions Ri and Rj, or whereby we call it R1 and Rj, are said to be adjacent if their union form a connected. Okay, so if we are talking about the region, okay guys, before this we talk about the pixel adjacent, remember? So this one is 4, this one is 8 adjacent, right? So in the region context, basically in the region example, we do have 6 pixel over here. So 6 pixel over there. Okay. The two regions, so this one is region, this one is region, are said to be adjacent if their union form a connected. So whereby the connected has been described clearly. Okay. So connected meaning the one that has been discussed over here. So here, we need to consider that we have 4 and 8 adjacency when referring to the region. So meaning, these two regions must have 4, adjacency and 8 adjacency at the same time for our definition, right? Okay. So whereby, if we take a look at this, so imagine this will be the example saying that you have one region and the other one is region number 2. Okay. So for example, the two region here, 1 and 2, for ones in figure D, okay, are adjacent only 8. So because the connection or the adjacent of the two region only happen by this 8. Okay, only happen by 1. So according to the definition in the previous paragraph, the one that we have here, 4 and 8 adjacency. So a 4 path between the two regions does not exist. Okay. So we don't have, unless we do have here this guys. 1. So then what we call it. This will be 4 adjacency. So their union is not connected set. So here, since we don't have the the 4 adjacency. So we might say that this union is not connected set, right? So that would be to ensure that the regional perspective. So the one that we had discussed before is the pixel perspective from here to the top. But here is the regional perspective. Sorry about that. Okay, so we need to be careful about that. Okay. Okay, right. And lastly would be boundary. So in E and F, so we have two things. The circle, I think you guys can read it. The circle point of the boundary, one value pixel, only if it adjacent between the region and boundary is used. Okay, so the inner boundary, so this one is the inner boundary of one value region does not form a closed path, so but is the outer boundary does. So that would be the idea of the boundary per se. Okay, for the example. All right. Okay, now we straight jumping to the distance measurement. Okay, right. So distance is basically the length between one point to another. Okay, that would be clear for us. So imagine that we want to measure the distance of a pixel. So somehow the pixel, let's say, it could be here, right? It could be here, 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 could be here. So it could be it could be horizontal, it could be vertical from here to here, and it could be this. So there would be many choices of measuring the distances. But by far, we need to be careful about the distances, whereby okay, so P is here, Q is here. Okay, so imagine that we have 3 location pixel located at X and Y for P, Q is U and V, WZ is for S pixel, right? So there must be 3 requirements obey for measuring the distance function, whereby we have P and Q. So distance of P and Q are larger than 0, whereby P and Q is 0 if P and Q is the same. So that would be the first requirement. So the second requirement is P and Q if we alternately change the like 2, 1 and 1, 2 is the same. Okay, example. Okay, so PS, so that would be 2 dimension. For this, P is here is taking up to the X and Y lah. Okay, so distance for P and S is basically the distance of, if we talk about S, this is Q, this is P, right? Okay, so distance between P and S, okay, is basically smaller or equal what we have here plus here. So that would be the requirement for saying that PS is equal or lesser from the sum of P, Q, and QS. So that would be the third requirement, right? Okay, Euclidean distance between P and Q is defined as this X minus Y because of this X and Y, and this one is U and V. So this one is distancing between having those things. I think the like the theorem Pythagoras that we have in the basic mathematical operation, right? Okay, for this distance measure, the pixel having a distance less than or equal to the sum value of R. Okay, so this would be the R, where the point contain a disk or R centered by XY. So we can talk about this somehow as R, right? Okay, so now speaking of the adjacency, path, connectivity, region, and boundary. So previously we done the discuss regards to the phi f something something 4 and 8 something something, right? Okay, so here we also have the d4 distance, whereby d is indicating for the distance by using the 4 city block distance. Okay, in this case, pixel having D4, okay, sorry for this, 4, distance for X is lesser than or equal to some value D, form a diamond. So this one is a diamond. Okay. Right. Okay. For example, the pixel of D4 less than 2. Okay. For the center from following the counter of the constant distance. So whereby D4 is 1 are the 4 neighbors of the X and Y. So whereby this, and this. Okay. So D4 is equal 1 are the 4 neighbor. So whereby if D4 is 2, what would be? Okay. So the way it is, let's say the way that we have this value is all about, imagine that we have 0, 0 at the center, guys. Okay. So this one is because of 0, 1. This one is minus 0, right? So this one is minus 1, 0. Okay, right? So this one is 1, 0. Okay. So in order to get 1 over there is how the pixel, imagine that we have this pixel, this pixel, this pixel, this. This is transposing the location, guys. Okay, for this. Okay, so based on D4 for P and Q, we will subtract them with this. Okay, let's say X minus U, right? So X minus U is 0 minus 1 plus 0 minus 0. So means 0 plus 1 plus 0. So 1. So that's the thing related to this one. So then we jump to here. So the center to the right. So 0 minus 0 plus 0 minus 1. So meaning 0 plus 1. So 1. So that would be reflecting to this value. Okay. So that would be the idea of getting the diamond, guys. Okay. And then same way goes to this and this. By having the city block distance for P and Q. For example, this one. How to get 2, guys, over here. So because of the location of that, of this pixel, imagine we have this, right? So what is the location of here? This one is minus 1, minus 1, right? Because of X and Y. Okay. So 0 minus 1 plus 0 minus 1. 0 minus 1 is 1 plus 1. There will be 2. So that's reason why from this pixel to this pixel, the distance of this 2 P and Q is stated as 2. Okay. So from that particular city block distance. So that would be the idea of calculating how D4 equal 1 and D4 equal 2 at a certain point, right? Okay. So we now having the idea of D8, also known as the chessboard distance. So the chessboard distance between P and Q is defined as the max. Okay, right? So how to do it? In the case of D8, distance X and Y less than equal the same. Okay, I think, for example, the pixel of D8 distance of minus 2 from following the counter distance as this. Okay, so D8, 1. Okay, D8, 1 is 1, 2, 3, 4, 5, 6, 7, and 8. 8 neighbor of pixel X and Y. So the idea is how to get this is the same as the one that we described in the previous slide. So imagine that we have 0, 0. So this one, guys, is 0, 1. This one is 0, minus 1. Okay, this one is minus 1, 0, 1, 0, right? Okay, this one is 1 minus 1. So this one is 1 plus 1. So this one is minus 1, 1. So So this one is minus 1. Minus 1. Okay, alright. So to do this, based on this equation, okay. So example, we take a look at this too. Okay, oh sorry, I need to change to green. So 0 minus minus 1. Okay, comma. 0 minus 1 with magnitude, and put it max over here. Okay, so 0 plus 1 is 1, and 0 minus 1 is also 1. So what is the max between 1 and 1? Obviously 1. So that's the reason why the value over here. Okay, so you can find the way that we have 2, 2, 2, 1, 1, 1, and so on as the chessboard distance by using this particular equation over here, right? I think that would be okay. Okay, right. So distance measure dm. Okay, for the case of dm, so just now we have d4, d8, right? Okay. So between P and Q is defined as the shortest. Okay, so only things need to be careful over here is right. This will be the keyword, guys. So in the case of the distance between two pixels will depend on the value of the pixel along the path. Okay? Along the path. So 1 and 2. A path as well as the value of the neighborhood. Right. So take a look at this example. Okay. How to measure the distances. Right. For instance, consider the following argument arrangement of pixels are assumed that P2 and P4. Okay, just imagine that this one, and 1, and P1 and P3 is 0. Okay. 0 or 1, right? See? So first thing, we try to put it as 0 at first. Okay. So I change it to blue. Okay, right. Okay, suppose that we consider the adjacency of pixel value 1. Okay, adjacency 1, meaning 1. We want to try to take a look at the path of 1 only. Okay. Okay, the first situation, case 1, P1 and P3 are 0, so meaning check. The length of shortest end path, or shortest end path will be this one, right? Shortest end path for DM. Okay. Between P and P4, so 1 and 2. Because of this one is 0 from P, 1 and 2. So meaning 2 lah. So that would be 2 over here. So take a look at the case number 2, guys. P1 is 1. So now we change this value to 1. Okay, hold on. I try to make things better. Oh, sorry for that. Okay, alright. Okay. P1, then P2 and P0. So P2 and P0 is no longer M adjacent. Okay, and the length of the shortest M path become 3. So why? Because of a P will be going here, be going here, and be going here. So that would be the shortest path, guys. So that would be 3 having this arrangement. Okay, similarly, when we comment apply to P3, so now we put it again at the different perspective. Oh, sorry. Now we change the value of P alternately. So just now is 0 and 1, right? So again, here, the idea of trying to find the DM is the same. So 1, 2, and 3. So that would be the same 1, 3. If we interchange the P1 and P3 at the same time. Okay. So finally, if P1 and P3 both are set to be 1, and we shall have the, sorry, the sketching as this, right? So the way that we have the shortest path is from P1 to P to P1, okay, P1 to P2, P2 to P3, and P3 to P4. So how long is the shortest one? 1, 2, 3, 4. So that would be 4 distance shortest end path between P and P4. So meaning from here to here, shortest. So 1, 2, 3, and 4. Okay. So because every single P on the given pixel having value of 1. So that we must go through every single each. Okay. So that would be the idea of having this one. Right. Okay, now we straight away jump to the basic mathematical tools. Okay. For here, okay, in this particular image processing lecture, there will be two things to be considered. To how to say to measure the pixel element wisely from one images to two second images. Okay, so we have element wise operation and we have the normal matrix operation. So be careful about this. So most and majority of the one that discussed over here is element wise operation. So element wise operation is happen to be symbol as this and this. Okay. So meaning element wise is basically straightforward to the pixel number 1 to 1, number 2 to 2, number 3 to 3, and number 4 to 4. So we have the element wise operation. But in the maths or in the common what we call matrices fundamentally, so matrix operation, we need to have this operation, right? So remember, this we multiply by this multiply by this, having this, right? And say that this and this, so we try to this and this, having this, right? So then again, to the green example, and here has this, and we have purple over here. We have this. So that would be the different things regards to element-wise operation with the matrix operation. Okay, so hopefully that we can differentiate between these two. So most or majority of the calculation happen over here is in element-wise operation. Right. Okay, this one is linear operation. I think this one is not so this is still manageable because of linear properties. I think it is happen in digital signal processing, if I may say. So in this particular subject, we did discuss about the additivity and homogeneity. Okay. So if the function of f1, okay, so in that particular topics, we call it function. So in this image processing context, we call it image 1 and image 2. Okay. So here, we don't use the a function, or what we call it. H is stand for in signal, we call transfer function. So anything, it could be DTFT, DFT, FFT, and so on. But the way it is happen in image processing, we translate them into the sum. Okay? Sum means element-wise sum. Okay. So having the sum for the whole image multiplied by the coefficient could be reflected to the end of the operation with the separated output image at the same time. So that would be linear, guys. Okay. So for the standard definition, a constant multiplied by an input, so this one is a constant, is the same as the output. So this one is a constant. is the same as the output. So input and output operation due to original multiplied by the constant. Even though we multiply them in input, so we also will gain the same properties in the output side with the same multiplication with the A and B. So whereby the F is the input while G is the output images. So that would be the simple way to describe linearity in image processing. So that's the thing. Okay, I think you guys should try this one at home. Basic mathematical tools for exercise. This one. So reflected to this one, guys. The one that we discussed in previous slide. For the image processing subject here, the simplest way to prove that the operator is nonlinear. Okay. Right. So the operator is nonlinear to find the example that fail the test in equation below. So equation means this one. Okay, this one is the max. Max of F1 and F2. Okay, so if we apply this concept of sum in the max, so say that we have max 0 minus 6, 2 minus 5, 2 minus 4, and 3 minus 7, right? So at the end of the day, if we try to put A is in front of the F1 and B in front of the F2, so at the end would be the output is similar as the one that we gain at this slide for linearity. Okay, so that would be one exercises to be made at home. Okay, right. So speaking of the arithmetic operation, so we have several operations to be done in this particular chapter number 2. So we have summation, difference, product, and division. So this is what we call is as image number 1. So this one is what we call is image number 2. Okay, so element wise, adding an image number 1 and element 2 will be regards to having S as a new image output. Okay, so same goes to this one. Image number 1 subtract with image number 2, we have the D new image as the difference of image number 1 and image number 2, same as the P and V itself. Okay, so that would be the idea of summation, difference, or what we call it subtraction, and multiply and division. Okay, so this is very important in the image processing itself. Summation, difference also, especially in order to enhance the quality of X-ray images. And multiply is happen in masking, guys. Remember the one that we have the teeth. So we talk about we multiply by a mask. So this one is black, right? So black is 0. This is 1. So the product of this images is the teeth, right? So less would be 0. Remember? So that would be multiply. Okay, image averaging is very powerful tools. So because in the normal perspective of image processing, so always we are trying to avoid from the noise. Okay, so this image containing the noise, right? So this one is the original image, this one is a noise. Okay, so this one is the output image. So in order to eliminate this kind of noise, so the idea of this concept to remove the noise is to averaging the pixel of this by having a new product of averaging the distorted images. So K depends on the K, right? So the K here is depending on how we set the value as a constant 5, 10, 20, 50, and 100, okay, to that particular noisy images. Okay, so this one is noisy image lah. Okay, so this one. So this one is the product from averaging of the noise image. Okay, all the images is 566 and 598, and all were scaled. So in the intensity, so span of intensity is 0 until, okay, so right, so this one is 2 power 8 of images, so meaning 0 until 255 intensity. Okay, right. So this one is variance, or this one is standard variance and standard deviation. Okay, so the moment that we, okay, so do you know the variance over here? So the variance is stated that how the difference between the original pixel with the noise added pixel. So the moment that we increase this k, so meaning the value k is rise up, so meaning the variance is become, when k is up, the variance is smaller, right? Because if you take a look at 100, 100, and 500. Okay, so this one is 20, right? So this one is 1. So the more the value of the variance getting smaller, so meaning the difference between the original images with the noise added images is not too far by definition of variance. Same goes to the standard deviation. So standard deviation is kind of things happen to be here and so on. Okay, so the one that half, second, and fourth. So that would be the different distribution issues. Okay, so here, so we can see the first one is this one is 5, this one is 10, this one is 20, this one is 50, this one is 100 by value of k, guys. So the moment that we increase the value of k, the moment we increase the value of k, so the variance is dropping down. So meaning the moment that we increase 5, 10, 20, 50, and hundreds, the clearer image that we have. So means the averaging effect is productive in order to averaging the pixel for avoiding the noise which has been added at the first place. So that would be the image averaging concept. Okay, so the k itself with the variance, right? Subtraction, I think we did discuss last week in class. Okay, setting the 0. So this would be the idea to the least significant bits in A. Okay, so the idea is this will be the original one. So this will be the setting all to 0 the least significant bit. So all the least significant bit has been set to by 0. And the difference between this and that is clearly mapped in C. Okay, so that would be good enough for having the operational as subtraction, because by using the original images with the least significant bits, we cannot see what is the satellite images stated, that what is the population, or what is the definition of trees coverage or water coverage at this particular map, right? So when we subtract those two things, in the eyes we cannot see well, but the improved image that we have by image subtraction, we can see that the most different things happen is at the joint of this river. Okay. Meanwhile, this we cannot see very well, this one, right? So that would be the idea of taking the advantage of subtraction in differentiating the intensity of pixel. Okay. Obviously, eyes is somehow being cheated by pixel. So that's the reason why subtraction is important here. Okay, same goes to image subtraction over here. The way that we decrease the DPI as concerned. So this one is this one is that, and this one is that. So just imagine that the the difference between the two DPI strategies on the first, on the second, and third, the less difference, the more nearer pixel is collapsing. So that's the reason why we cannot see the edges over here, because the DPI is coming closer to the higher level, right? Okay. So one more thing is the image subtraction of so this one is angiography. I think A is the mask. Mask is happen to be the reference images. So this one is the real one, real images, and this one is differences between this and this. Okay, so basically, if we try to subtract mask and real data that we gain from the experiment, we can't see the clear picture of the wanted result. Okay, so but when we enhance the differences between the images, so we can see the clearer things that happen in between of the vessel blood, okay, especially here. So that would be the powerful of subtraction in image processing, whereby we need to enhance the differences between image and images. Okay. Okay, multiplication, as I did mention earlier here, okay, here is the multiplication, guys. The one that we do for image 1, and this one is image 2, so this one is output. Okay, the way it is, when anything pixel intensity multiply with 0, this is 1, so the output will be 0, right? So say that this is 0.5 times 1, so there will be 0.5, right? So that's the reason why the remaining teeth portion or teeth location in the mouth will be remain at the output side of the images. So that would be the impact of multiplication. So cancelling every single thing below than 0 and appearing all the thing equal to 1. Okay. Okay, logical operation. This is the way that we talk about. We try to invite the Boolean expression, or what we have logic operation in the image processing. So whereby this is talking about the B and this one is not B. So meaning every single thing in B and not B is this way. So B and B, N would be this portion. The intersection between image number 1, B1, and image number 2, B2, right? So this one is union, and this one is and not and XOR. Okay. Okay, this one is one example of basic mathematical mathematic tools. So yes, okay. So take a look over here. Original image, X-ray. Image negative obtained using grayscale. Okay, this one is, let's say this is B, and this is this complement of B. Okay, so this is complement of B, meaning if the area stated as white over here, it will be black over here. If the this image one stated as 0, and it will be white over here. Okay, the union of A and the constant and a constant image. Okay, right. So in order to portray the main parts of human bone, okay, so basically the union of the image, so A and okay, a constant meaning we try to unite. Union is this one, right, guys? Okay, some value in order to make things pop up clearer. So whereby say that the z, okay, z is the intensity for this particular case, x, y, z. So 3 times. Okay, so meaning 3z appears value from a. So anything appear it more than 3z will be appear in this output images as a gray. So that's the reason why anything less than that will be gray. Anything more than that is reflecting to the original bone images. So that would be the idea of uniting A and B with maximum Z. Z is basically setting of constant, guys, over here. So whereby we can have the gray is in the middle of 1, right? So let's say 0.5. Okay? So that would be the idea of changing the paradigm to see the X-ray images. Okay. Okay, so I think this would be the last sub chapter in the chapter number 2, spatial operation. So the one that we discussed earlier is mathematical operation and so on and so forth. So this is spatial operation. Spatial means, remember, the tiny pixel or a group pixel or geometrical. So geometrical means, let's say this is T. So what is the T if we try to rotate them into anti-clockwise? So that is the transformation of geometric spatial. So neighborhood operation is the group one. Single pixel is this one. So we have single pixel operation stated by this one, guys. Okay, so imagine that we have this one is 0, okay? So when we try to make the single pixel of spatial, so the value of 0 input will be reflecting to the value of 255 as an output. So that's the reason why we have 255 over here based on the opposite graph for the single pixel operation over here. So when we give 255 means white in the input images, but as the output will be black, 0. So example, this is 255. So when we transform it, will be 0. So that will be hitam over here. Okay. Right. For the neighborhood operation, we have the idea of averaging every single thing. I think GX is the new output pixel. So whereby this is FRC, it reflecting this, while M and N is a group of surrounding the original pixel. Okay, so example, this is 50, this is 50, this is 25, 25. So the averaging of all the pixel centered by 25, 25 is happen everything. So it is mostly used in a mosaic application. Okay, so for this, so you can see that happen. We have, let's say this is human, and we set 25, 25, and this image will be blurred because of the averaging of the pixel, right? Okay. Okay, so the third one is geometrical spatial transformation. So we have a fine matrix. So therefore we have this. So we have several one, either scaling, rotating, translation, shear, and shear vertically and shear horizontally. So it depends on how we want to manipulate the images from the original to the to rotate them in other way around. Okay, based on the affine matrix that has been applied with the original pixel. So this one is the original pixel one, guys. Okay, so here is basically the one that we did discuss in previous chapter. Remember bilinear and bicubic. Remember the one that we did discuss about zooming? I think in last video. Okay, so the bilinear we have by cz plus d. Remember, while this one we have ij. Okay, so this one is in the cubic, and this one is the bilinear. So you just imagine that we have the clear picture of the, how to say, okay, C, example C. So this one is bilinear and this one is bicubical. So bilinear, bicubical, and the B is intensity assignment. Okay, nearest neighbor. Okay, so this one is the original. So say that this one is nothing changed, meaning in the pixel way, we have a majority of the pixel. Say how many pixels of those? Okay, I think 2, 3, 2, 4, 3, 2. Okay, let's say this is 10 pixel, eh? Okay, so this is 10. So we can see that this one is nice, obviously a straight line. So this one is kind of edgy, okay? And this one is slightly edgy compared this, because this one is, if the edges or if the pixel happen to translating darker, intermediate, and light like this frequently in the edge, that would be a better for the geometrical. So we can see over here there will be more pixel of having several intensity in bicubical compared to bilinear, right? So that's the reason why bicubical is better than bilinear in the transformation concept of spatial. So that would be the one example happened in from the last video, the one that we discussed earlier. Okay, right. So I think that's all for this video. I hope you guys can rewatch the video and do some exercises given in this particular part 2 video for chapter number 2. So I'll see you guys on the next chapter number 3. See you soon and bye. Okay, thank you guys for watching NMZH channel. Hopefully you can get knowledge and benefit from the videos. Thank you so much. Assalamualaikum.